Physics addresses one central question: how does the universe work? For centuries, the answer appeared straightforward. Reality was an interlocking machine. On a human scale, everyday motion is calculable. If you roll a tennis ball across a field, you can measure its speed, the friction of the grass, and predict exactly where and when it will stop. These rules apply even as systems grow in complexity. Picture a speeding steam train. If you stand inside a passenger car moving at 50 miles an hour and jump straight up, you land in the exact same spot on the floor. Relative motion is a solvable equation. Early scientists, led by figures like Isaac Newton, built a framework around these observations called classical physics. They believed these mathematical laws governed every corner of existence. In this view, the universe is a predictable clockwork machine. If you know all the exact variables of an object today, you can determine its location tomorrow. As technology improved, scientists looked past the scale of planets and tennis balls. They zoomed toward the tiny building blocks of reality. There, they found that when examining atoms and subatomic particles, the trusted mathematical rules of classical physics stopped working entirely. The predictable machine of the universe appeared broken. None of the old math could explain how these tiny particles moved or interacted, a crisis that forced the birth of quantum physics. This shift started with a problem involving the relationship between heat and light. When you run electricity through a metal filament, a portion of that heat converts into light, providing the glow inside early light bulbs. This temperature gradient chart shows the mathematical dead end scientists hit. Classical equations dictated that a superheated metal should shift through the visible color spectrum and eventually emit invisible ultraviolet light. By that logic, a hot enough light bulb should become invisible to the human eye. In the late 1800s, Max Planck developed a theory to fix this mathematical impossibility. This diagram compares the old theory with Planck's solution. He proposed that light and energy do not travel in a continuous, smooth wave. Instead, they travel in distinct, individual energy packets called quanta. Albert Einstein later expanded this idea, proving that light acts as both a wave and a stream of individual particles simultaneously. The solution to the light bulb problem revealed that reality operates in discrete chunks. As physicists investigated these individual packets further, the universe began to look increasingly strange. This schematic shows the setup for the famous Double-Slit Experiment. It features a particle emitter on the left, a barrier with two vertical cuts in the middle, and a detector wall on the right. In phase 1, if you shoot solid objects, like tiny bullets, through the barrier, they travel in straight lines. They hit the back wall and form two distinct impact bands. In phase 2, liquid waves are sent through those same slits. The waves break apart and overlap, creating a complex, multi-striped interference pattern on the wall. In phase 3, scientists fired single electrons. Despite being solid particles, the electrons produced a complex wave pattern, acting as if a single particle was traveling through both slits at the same time. Scientists then placed a measuring device next to the barrier to observe exactly which slit the electron was passing through. The moment the electron was observed by the detector, it stopped acting like a wave. It reverted to acting like a solid bullet, forming just two bands on the wall. The act of measuring the quantum world changes its behavior. This discovery challenged the classical idea of a predictable, independent universe. This is explained through superposition. It is a principle stating that an unobserved electron exists as a wave of probabilities, occupying multiple states and locations simultaneously. The moment an observer looks, that wave of probabilities collapses into a single physical reality that we can measure. The many worlds theory suggests that when a quantum probability collapses, all other possible outcomes don't vanish. Instead, they occur in newly created parallel universes. Alternative theories focus on quantum entanglement dating back to the Big Bang, suggesting that because everything was once connected, the spatial separation between objects is an illusion. While these concepts sound like science fiction, they are genuine attempts by physicists to make sense of a reality that is far more fluid than our everyday senses suggest. Humanity still explores why the quantum world behaves this way, yet the mathematical formulas developed from these theories work reliably in practice. Harnessing these microscopic rules allowed engineers to build the foundational technology of the modern world, starting with massive early computing systems. The smartphone or computer you are using right now relies entirely on our understanding of quantum physics to function. The predictable clockwork machine we once imagined was really only the very first chapter in our understanding of reality. Physics is the mathematical language we use to decode the deepest, strangest mechanics of the universe.